So today I thought we would finish up our use of derivatives to help us graph functions and also finish up MaxMin problems. So that's kind of a big thing to be, two important topics, and we will end them today. So one type of function we have not talked about yet is a radical function. We talked about rational functions in the last video. Radical functions are functions that have radicals in them, like the cube root of x. So usually, the first thing you're going to do is get rid of the radical sign, because all our formulas don't have radical signs for taking derivatives. So we change that into x to the 1/3. And one nice thing about radical functions is we don't have to worry about asymptotes like we did with rational functions. So we sometimes have to worry about domains, but when you're talking about a cube root, we can take the cube root of any number. So that's not a problem. If you're talking about square roots or fourth roots, then you might have to think about restricting the domain. But all that does is really make your job of graphing easier, because you don't have to look at as much of the graph. So anyway, we'll deal with the cube root of x. So we can go straight to taking derivatives. So we use the power rule. So it's nx to the n minus 1. If you really want to be able to analyze that, it's sometimes better to get rid of negative exponents. So we want to see where the derivative is 0 or undefined. Well, there's no way you're going to make that fraction equal to 0. But you are going to be undefined at x equals 0. So the only critical value is x equals 0. So if we put that on the number line, we see if you take any number and take the cube root of it, but then square it, it's always going to be positive. So that means anywhere except at 0, the derivative is positive. At 0, I might want to make a little reminder that at 0, if I put a really small number in here, that's going to make the derivative really large. So we're talking about an infinite slope. So I'm just going to remind myself that. So I can say there's no local maxes or mins. The function is always increasing. So y of x is always increasing. So even though we didn't find any special points, we did find out quite a bit about the function. Now, let's go to the second derivative. Second derivative, we can work from here, again with the power rule. So we get negative 2/9 x to the negative 5/3, which is negative 2 over 9x to the 5/3. And I want to see where that's 0 or undefined for possible points of inflection. Well, if I put the second derivative on the number line, again, there's no places where this is going to equal 0. I can't make 2 into 0. But 0, again, is going to make it undefined. But this time, if I take a negative number and take the cube root of it and then the 5th power, it's still going to be negative. So I get a negative divided by a negative is positive. But if I take a positive value of x, I'm going to get a negative derivative. So I see my function is going to go from concave up to concave down, because the second derivative is going from positive to negative. So we do have, at 0, 0, a point of inflection. And that turns out to be the only important point on this graph. And now we're ready to graph it. We know we have kind of a infinite slope right here, so I'm going to put that in. And I know the function is always increasing, and it's going from concave up to concave down. So So it's going to go something like this. Increasing in concave up to increasing in concave down. Now, it may not be perfect, but that's going to be a pretty good sketch of what x to the 1/3, the cube root of x, looks like. Okay, well, let's take another radical function. This is the x squared, and then you're taking the cube root of it. So this is really x to the 2/3. And again, you're taking a cube root, so you can take the cube root of any number. So you don't have to worry about your domain. It's going to be all real numbers. So right now I can just go straight to taking a derivative. 2/3 x to the -1/3. Again, we're using the power rule. Or 2/3x to the 1/3. We're at that same old spot again. This happens often in radical functions, where the only critical point is when the denominator is equal to 0. There's no place where this equals 0. But it is undefined at x equals 0. So that is a critical value. And the cube root of a negative number is negative, and the cube root of a positive number is positive. So I can see the function where the derivative is negative is decreasing and then goes increasing. So I see at 0, I have a local minimum. And if I put 0 into here, I get 0. So again, that's the origin is going to be a special point. And this is a local minimum. And there's no local maximums, as we can see from there. And we do know, again, that the derivative at this point is an infinite slope. It's not a zero slope like we found in polynomials when we found our zero derivatives. So now we go to the second derivative. Again, using the power rule, -2/9 x to the -4/3, or -2/9x to the 4/3. Again, if you set it equal to 0, you're not going to find any place where it equals 0, but it's undefined at x equals 0. So that's my only critical point. And I kind of know it's not going to be a point of inflection because I already found out it's a local minimum, but I still want to know something about the concavity. Well, if you take the cube root of any number and then the fourth power of it, that fourth power is going to make everything positive. So that means the second derivative is always negative, which means the function itself is always concave down. I think we found out there's no points of inflection. There's one local minimum. It's going from decreasing to increasing, and you kind of have an infinite slope right here, always concave down. So this time it's going to go decreasing and concave down until you get to the origin, up to a really steep slope. And then it goes concave down, but increasing from that really steep slope. So that's what x to the 2/3 would look like. So radical functions aren't too bad, especially if you use the first and second derivative to help you tell what the graphs, whether they're increasing or decreasing, and what their concavity is, and finding any kind of special points. Okay, so enough for radical functions. Why don't we take one trigonometric function that's considered, if you haven't already done it a lot of times, a pretty hard function to graph, the tangent of x. And I think you all know from your trigonometry that the tangent is equal to the sine over the cosine. So it looks a little bit like a rational function. It's not really, because these aren't polynomials, but maybe it's going to have vertical asymptotes. It's not going to have end behavior asymptotes like rational functions, but you are dividing by a function. And if that function is ever 0 and the numerator is not 0, you're going to have vertical asymptotes. So what makes the cosine 0? Well, pi over 2 does. So we know x equals pi over 2 is going to be a vertical asymptote. And also at 3 pi over 2 and at negative pi over 2, there's asymptotes all over on this function. What else could we easily plot? Well, we know that y is going to be 0 when the sine of x is 0. So that's going to be, we're going to have points at 0, 0, and pi, and 2 pi. So that's a starting point. We still wouldn't be able to graph it too well. So let's take the derivative. Well, the derivative of the tangent, we proved, is the secant squared of x. Well, the secant squared means you're taking the secant of x times the secant of x. So that means it's always going to be positive or 0. So what does that mean? There's going to be no local maxes or mins. The function is always going to be increasing except at the places where you have a 0 derivative, whenever the secant is equal to 0. But the secant is 1 over the cosine. So you can't get 1 over something ever equal to 0. So basically we're never going to have any places where the function actually levels out to a 0 slope. So I can just basically say that y of x is always increasing. That's going to be something nice to know when we go to graph it. Now we can go to the second derivative. This is going to be a little more difficult, but we're going to take the second derivative by taking the derivative of that. So we've got to use the chain rule. The main function is this function squared. So the squaring function, the derivative of x squared is 2x. But we have a different function in here. So we have to put that function and then multiply by its derivative, which is the secant of x tangent of x. So we're bringing back some of the formulas that we learned about the trig functions. Well, this is 2 times secant squared of x times the tangent of x. And I want to see where that's 0 or undefined. Well, that's a little tougher, but if we think, we already analyzed that the secant squared is always positive and never 0. So really, it's all going to be up to the tangent of x. And we already know where it's undefined, and we're not going to have local maxes or mins there. So basically, we can see that the tangent of x is equal to 0 when the sine is equal to 0. So if we put it on the number line, the second derivative is going to be 0 at 0 and pi, and 2 pi, and negative pi. And we're also, maybe, since it's going to be undefined at the tangent of x, sine over the cosine at pi over 2, we could put those values of pi over 2 in here. So basically, what do we know? That this is always positive. The tangent, which is the sine over the cosine, is positive when these are both positive and when they're both negative. So we're talking about the first quadrant and the third quadrant. So we know in the first quadrant from here and in the third quadrant, we're going to have a positive second derivative. So it's concave up, and we know it's always increasing. So you can see that it's in these areas it's concave up and increasing. And it's also going to be true when you're at negative pi and negative 2 pi. Now it's going to be concave down whenever the tangent of x is negative. And that's going to be in the other quadrants. So from pi over 2 to pi in the second quadrant, it's increasing and concave down. And the same thing is true here. And you've got a graph of the tangent of x. Oops, I missed one. So anyway, just shows you one more time, and that's the last time we're really going to talk about using derivatives to help graph until we get to the last chapter when we learn about some new functions. Okay, so let's finish up max-min problems, a really important type of problem. And I came up with one that will have some radical functions in it. So, a semicircle slab of gold of radius 2 meters is uniformly 1/4 meter thick. We get to keep the largest rectangle we can cut from this gold slab. Sounds like a good deal to me. So basically, since this is a semicircle, what really defines it is its center, so I should probably put in the center, and now I get to make my rectangle. Well, I'm gonna see if I can make the largest rectangle I can. This is a maximization problem. So I'm gonna try like that. Well, what are my dimensions? Well, I'm gonna call the distance from the center to this x. And I'm going to call this distance y. And that's going to determine what my rectangle is. And I'm going to try to maximize the area of this rectangle, because the third dimension is already determined. It's uniform thickness. So if I can maximize this area, I'm going to maximize the total volume. So what is the dependent variable I'm going to call area, and it depends on x and y. And it's going to be this dimension, 2x times y. But we want to get it down to just one variable. So I can always, in a circle, draw in a radius. So I'm going to draw in that radius. And what do I know? By Pythagorean's theorem, x squared plus y squared is this side squared. So this is the square root of x squared plus y squared. And here comes our radical in our function. So now we just have x, because y is equal to, we have this relationship, but I don't really want both of those in there. And I know that this radius is equal to 2. So it's really y that I'm going to want to get rid of. So I say y is equal to the square root of 4 minus x squared. I don't really want to throw in an x squared plus y squared. And that's really the radical that shows up. And what's our domain? Our domain, x is a distance, so it's got to be greater than 0, and can it ever get as big as the radius? So it's got to be less than 2. So that's what I have to work with. Now we don't know how to do formulas of derivatives with radicals in. So the first thing I'm going to do is write that as 4 minus x squared to the 1/2. And you can see at this point that I'm going to have to do a product rule, because I have a function times a function. I like to take my constants out front. So I have the first function times the derivative of the second. I have to use the chain rule here. A lot of good practice in these problems. 1/2 times 4 minus x squared to the negative 1/2, but then times the derivative of this inside function, which is negative 2x, plus the second function, 4 minus x squared to the 1/2, times the derivative of x, which is just 1. See if we can do some simplification. So I have my derivative. What can I factor out of these two terms? First of all, it'd probably be good just to multiply the 1/2 times that, and then I can see that I can take out a 4 minus x squared, and the lowest power is the negative 1/2. You always take out the lowest power. So what do I have left? Negative x squared, and then plus this to the first power. And if I just write it in a little nicer way, I can go 2 times 4 minus 2x squared, getting rid of that negative exponent. I can write it like that. And where is that 0 or undefined? Well, it's going to be undefined at any values of x that are greater than or equal to 2 or less than or equal to negative 2, because I can't divide by 0 and I can't have square roots of negative numbers. But luckily our domain avoids any of that. So it's never really going to be undefined in our domain. But it's going to be 0 when this equals 0. So when 2x squared equals 4, or when x squared equals 2, or when x equals plus or minus the square root of 2. But minus the square root of 2 is not in our domain. So my only critical point is the square root of 2. Well, I can only go from 0 to 2. There's the square root of 2. Here's my derivative. And since this is always positive and this is always positive, when x is close to 0, this is positive and this is negative. So you can see that we do have an absolute maximum when x equals the square root of 2. So I pretty much finished this problem. I know what to make this, but let's find out what my total area is. The area is going to be 2 times the square root of 2, and then what is y? Y is 4 minus the square root of 2 squared. So it's also the square root of 2. So altogether we get 4 square meters. Now if you really wanted to turn that into a volume to find out how much it's worth, we can multiply it by the thickness, which is 1/4 meter, so we can see we get 1 cubic meter of gold. So I think we're doing pretty well. That's about, I looked this up, and that's about 42,500 pounds of gold. And at today's current value of gold, it works out to be a little bit over $750 million. So I think that was a pretty worthwhile use of MaxMin problems. Somebody who didn't know calculus probably would have picked the rectangle to look like this and wouldn't have done nearly as well as us. Okay, so let's just finish this up. I promised you a few videos ago that we were going to talk a little bit more about maximizing profits if you're in a company making something. This is an economics problem, and I already went through the rationale a little bit, but basically we're trying to make widgets. So I'm going to let x equal the number of widgets, and up here we're going to put the cost to make the widgets and the revenue we make for them. So I'm going to graph two separate things. Well, I discussed before that if you make no widgets at all, you've already got your manufacturing plant, you've already hired somebody, you probably have a fixed cost. And those first widgets you make, because you've hired somebody, are going to cost quite a bit. So you have a high, what we call marginal cost. The slope of the cost curve is high, but then as you get more efficient, your cost per widget gets less. It levels out. It never is going to go down as you make more widgets. But then all of a sudden, as you get maximum efficiency and you try to push it farther, your marginal cost goes up and it costs you more. Machines are breaking down and you're paying for overtime. So this would be like a typical cost curve. A revenue curve, if you don't sell any, you don't make anything. But often you can sell those first you make at a fairly high revenue per item. So the marginal revenue is pretty steep at the beginning, but then to sell more of them you have to bring down the cost or the price, and your revenue goes down. So a revenue curve might look something like that. So I've drawn this for you once before, but what if we want to maximize profit? And that's usually what you try to do. Well, the profit is a function that depends on x, the number of widgets you make. So the profit is the revenue, how much you bring in, minus the cost. So how would you take the maximum of that? You would take the derivative. You get r prime of x minus c prime of x. And you would set that equal to 0 or undefined. And usually there isn't any place where these curves have an undefined derivative. They're usually fairly smooth. So basically, it's going to be when r prime of x equals c prime of x. And this is what I showed you kind of before on the graph, and now we've kind of proved it. But right here, where the marginal revenue equals the marginal cost, that's where you make the most money, where your revenue is so much more than your cost. Of course, we didn't prove max or min, but you can also see that you get your minimum profit when the marginal revenue equals the marginal cost. So you would want to pick this place over here where the derivative is 0, where your marginal revenue is greater. When your revenue is greater than your cost. So that's something that you see in an economics book, that maximum profit happens when marginal revenue equals marginal cost. So we've kind of proven it here with calculus. So I'm hoping you see as we go through the year that calculus has applications all over in this world, in the business world, in the engineering world, in the science world especially. Well, good. Well, we're almost done with derivatives. We have one more really important topic to do, which we'll cover in probably the next 2 videos. It's important enough, just like max-min problems. We're going to learn how to do another important application of derivatives. So, good. I'll see you in the next video, I hope.